All right, welcome back to week 8. We are almost there. This is the last assignment, and then next week we will have a test. So last week we talked about independent events, which were events where the probability didn't change, it stayed the same, something like flipping a coin, spinning a spinner. Anytime we're dealing with a percentage for a probability, we would say that's an independent event because that percentage isn't going to change. It stays the same from one event to the next. This week, what we're going to talk about are dependent events. And dependent events, you can probably guess, are when the probability is going to change from one event to another. So you can look at this cooler full of cans of pop, Coke and Sprite, right? And you can imagine that if you grab a can of Coke out of that cooler, there is one less can in that cooler. And so that's the idea of a dependent event, because once you take one out, it changes the quantity of cans in the cooler, and so the probability is going to change as well. So let's just jump right into this example so we can see what's going on. So it says, suppose you pick a soda. It's either soda or pop, right? Depending on who you are. Suppose you pick a soda out of the cooler pictured to the right. There are 12 Sprites and 22 Cokes. What is the probability you pick a Coke? Well, the thing we have to think about is we want to create a fraction that has the total on the bottom. And in this case, we're asking about the probability of picking a Coke. So we would put Coke in the numerator. All right, and so since there are 12 Sprites and 22 Cokes, well, that means we'd put a 22 in the numerator of our fraction, and then the total goes in the denominator. So 12 plus 22 is 34. Okay, and so that is how we can find the probability of picking a Coke. There's 22 cans of Coke, there's 34 total cans, so it's 22 out of 34. And we should probably go to our calculator and do 22 divided by 34 and see what we get. We get 0.647. So I'm going to go ahead and write that down as my percentage, right? So actually, let's go decimal. And then we can turn that into a percent, 64.7%. Okay, so if you grab a random can out of the cooler, I don't know if many people do that, but there's a 64.7% chance you're going to get a Coke. All right, now, suppose we are going to take a second can out of the cooler. What's the probability of getting 2 Cokes in a row? Well, we're going to do the same thing where we have Coke out of the total, right? And so we know the first fraction, it's still going to be 22 out of 34 because we're starting over again. There's all the cans are back in there, right? And so this is our first pick, 22 out of 34. Now the second time, if we want to get another Coke, we have to think about what happened. We took one can of Coke out, so that means that now there are only 21 cans of Coke, and there are only 33 total cans. Okay, and so we have to multiply these two fractions together. Okay, and let's go ahead and do that. So we have 22 times 21. Let's go over to our handy calculator. 22 times 21, that's 462. And then let's do the other one, 34 times 33. Yep, 1,122. And you might think, wow, these are really crazy big numbers, but it doesn't matter because we're just going to use a calculator to do the calculating. So we have 462 divided by 1,122, 0.411. All right, so we have 0.411. And so we can move our decimal and create a percentage of 41.1%. So the probability of picking 2 cans of Coke in a row out of the cooler is 41.1%. Now, same thing. This case, it says you're starting over all the cans are back in the cooler. What's the probability of getting 3 Cokes in a row, right? So now we have to think this first fraction is going to stay the same. Now the second one will be the same as what we came up with before, but the third one, you could probably guess, it's going to be 20 over 32. Okay, so we just are reducing each number by 1 because the first pick there were all the cans there, and then each time we take one out, we have to reduce each number by 1. Okay, so we have these 3 fractions that we need to multiply together. Now, I'm wondering if I could do all of these at once. Let's try it. If you use this calculator, let's try this. 22 over 34 times 21 over 33 times 20 over 32 equals. Wow, look at that. So if you want to use this calculator, if you have this one, I would do it, because that's a lot faster than multiplying the tops, then multiplying the bottoms, then dividing. So we have 0.257. So 0.257. Now, I might not be getting the right number of decimals based on what you have to enter in Schoology, so you may need to use a different calculator if you want more decimals. All right, and so this, if we move the decimal, it's 25.7%. Okay, so if we want to get 3 Cokes in a row, there's a 25% chance we're going to do that. So that's the idea of dependent events, multiple dependent events. It's multiple events, if we define it, where the probability changes because we are taking stuff out, right? Anytime you're reducing the quantity of something. Okay, so it's multiple events where the probability changes. Okay, so grabbing cans out of a cooler, eating candy out of a bowl. You don't put the candy back after you eat it, right? So that's the idea. The probability changes because the quantity of something changes. All right, so here we go. Got a little pattern thing here. I wonder what this is. Do you notice a pattern? If below is the first probability of a dependent event that will repeat 5 times, fill in the rest of the fractions and find the probability of the multiple dependent events. Oh, the person who made this does it a little differently. They multiply by 100. We're going to get rid of that because we didn't do that. Let's get rid of the multiply by 100 part. All right. So, well, just think about it. What happened in the first 3 examples that we did? Well, every time we picked another time, the numbers reduced, right? Let's fill in the probabilities then. If so, 30 over 50, well, that means this is going to be 29. And we can just follow the pattern, 28, 27, 26, and then we have 49, 48, 47, 46. Okay, and we're going to ignore that multiplying by 100 part. If you want to know, the multiplying by 100 part is the same as when we say, hey, move the decimal 2 places. Because when you multiply by 100, it'll move that decimal 2 places for you. Okay, so let's go over to our handy calculator and see if we can do this. All right, so we have 30 over 50 times 29 over 49 times 28 over 48 times 27 over 47 times 26 over 46. I think that was it. Did all the numbers? Yes, they're all good. 0.067. All right, so we have 0.067, and if we move the decimal 2 places, whoops, I don't have enough room. 6.7%. Okay. All right. So then we have another one here that says it'll repeat 3 times. What? Fill in the rest of the fractions. Find the probability. Well, this would be 9, 8, 7, 19, 18, 17. So if we go over there and, here, on this one, I'm going to actually show you what happens when we multiply by that 100. Whoops, I forgot the numbers already. What are they? 9 and 19. All right, here we go. So we have 9 over 19 times 8 over 18. Uh-oh, that first one might show up as a 14. And then I'm going to do times 100. If you want to see what happens when we do times 100. It makes that into our percentage instead of a decimal. So it's 11.764. And if we keep to the nearest hundredth, that would be 11.76. Uh-oh. You'll notice that that first number was a 14 instead of a 19. We got to redo this. Do it again. 9 over 19. 8 over 18. 7 over 17. Times 100. Uh-oh, that 17 might show up as an 11. Dang it, it did. Here we go. Let's do it again. 9 over 19. 8 over 18. That's the only problem with this calculator. 7 over 17 times 100. There, it worked. There we go. 8.668. So that 8 means we have to round that second 6 up to a 7. So we're going to say this is 8.67%. Okay? So we have 8.67%. All right. There we go. So that's how you can use that 100 if you want. I should probably get rid of this because we actually did multiply by 100. There we go. Okay, so here we go. Another example. A teacher has 32 calculators. 8 of them are broken. You decide to be nice and grab 3 calculators at random for yourself and your 2 neighbors. What is the probability that all 3 calculators work? That means they're not broken, right? Well, first thing we have to figure out is 32 total, right? Whoops, I need a pen. 32 total. 8 broken. That means if we subtract that 8, we end up with 24 that work. Okay, so that's kind of one thing that we're going to have to do is sometimes figure out the quantity of different things. And so we're grabbing 3 calculators. We want to know that all 3 of them work, right? So we're going to say work over total. Okay, and so work over total means that we have 24 out of 32, and we're going to do this 3 times, right? And each time we're going to reduce our numbers by 1 because we're grabbing a calculator out, and that means there's 1 less calculator in the box. Okay, so there we go. We're going to do the math on that. So we have 24 over 32 times 23 over 31 times 22 over 30, and I'm going to throw in the times 100 because it helps with the decimals a little bit. 40.806. That 6 says I have to round that 0 up to a 1, so it's going to be 40.81%. All right, so here we go. I'm going to put in the times 100, and it's 40.81%. All right, there we go. So there's a 40.81% chance you're going to grab 3 calculators that work. And that's a fairly high percentage because there are more calculators that work than are broken, right? Okay, same question. You decide to be nice and grab 3 calculators at random for yourself and your 2 neighbors. What is the probability that all 3 calculators do not work? All right, this case, instead of work, we want do not work, or they're broken, right? So that means it's 8 out of 32. Times 7 out of 31 times 6 out of 30. Okay, so let's go do the calculating on that. 8 out of 32 times 7 out of 31. Uh-oh, that 32 looks kind of funny. Hopefully it works. And I'm going to do times 100. Yeah, they all worked. 1.129. So if we think about rounding that 2, because there's a 9 next to it, that 2 becomes a 3. So it's 1.13%. And you'll notice this is a really small percent. Times 100 equals 1.13%. So pretty small because the numbers we started off with that were broken were really small. 8 out of 32. And when we multiply decimals, they get smaller and smaller. All right, so this one, you could take a minute to look underneath your desk to see if this is true. There is lots of gum underneath these desks. But see if you can figure this one out. And remember, since it's in the red box, you're going to have to put it into Schoology. And when you're done with this, Why don't you pause the video first, and then when you're done, start it up again, and we'll do some more examples. Okay, here we go. How many do we have? Just one more. All right. Congress. They make our laws. So right now we have 48 Democrats, 50 Republicans, and 2 independents. Suppose a lobbyist for Amazon randomly selects 3 senators to sweet talk. Well, do you know what that means? They're trying to convince them something. So when you sweet talk somebody, you're trying to convince them to do something for you. So what is the probability that all 3 are Democrats? Okay, so we need something here. We need to know what the total is. So we have 48, 50, and 2. If we add those together, we get to 100. Okay, so our total is 100. We want to know what the probability that all 3 are Democrats. So we're going to create a fraction. Democrats over the total. Okay, so we have 48 Democrats. So we have 48 out of 100. And we're talking about 3, so we create 3 fractions. 47 over 99 and 46 over 98. And then times 100. All right. Handy dandy calculator coming up. 48 over 100 times 40. Hold on. 48 over 100 times 47 over 99. The thing is, if you pause with this calculator, oh no, I wrote it wrong. I can't talk and do this at the same time. 48 over 100. If you pause, it's going to calculate, and you don't want that. I did it again. I wrote 64. Hold on. 48 over 100. 47 over 99. 46 over 90. Oh, no. Didn't do it. Equals. No. Dang. All right, here. I'm having trouble with this one. Whoops. Hold on. Right there. That's what we want. No, it says 48. We want to do this again. Dang it. Whoops. Writing with my hand down here. 48 over 100 times... Uh-oh. Low battery. Better get this. 48 over 100. 47 over 99. 46 over 98 times 100. There we go. Whew. That took a while. 10.696. Ooh, this one. That 9 has to be rounded up, but we can't go up to a 0 without changing the 6 to a 7. So it's 10.70%. All right, so here we go. 10.70%. Okay. We can do this, even though we've got 10% of battery left. Actually, you know what? I got a cord here. I'll just plug it in. Plugging it in. There we go. All right, second question here. Congress is currently made up of the same group, 48 Democrats, 50 Republicans, 2 independents. Suppose a lobbyist. Same question. What's the probability all 3 are Republican? Well, in this case, we want to think Republican, and there are 50 Republicans. Ooh, 50. That's a little easier number to work with. So we have same thing. Now we're going to say Republican over total. So it's 50 over 100 times 49 over 99 times 48 over 98 times 100. Okay, let's see if I can get this one in there better than I did before. Too bad I can't just go edit that. Okay, so we have 50 over 100 times 49 over 99 times 48 over 98 times 100. Uh-oh, I think some of these are going to goof up. No, they all worked. There we go. 12.121. All right, that 1 means we leave the 2 alone, so it's 12.12%. There we go. All right, you have one to do on your own about Harry Potter. This is one that you need to enter into Schoology, and then you have a challenge one that I suggest you try. It's about a deck of cards. If you think about a deck of cards, there's different numbers of cards and face cards and different suits and all that, so you can do all kinds of probability with that. So give it a try.